we are very far from being able to predict what we're going to see until we see it. Anything could happen.
It's built and it's ready to fly, and for me it's been a part of almost all of my career. 23 years is a long time to get to work on one project of this kind.
And there were those that argued that it couldn't be done.
It's the largest, most advanced, most expensive space telescope ever made. The James Webb Space Telescope. The product of decades of research, design, and innovation. This huge machine is built to look further into the universe than ever before. The James Webb Space Telescope is designed to nothing less than revolutionize our understanding of the cosmos. It has three main missions: to see the earliest light from the Big Bang, to study the formation of galaxies and stars, and to look for signs of life around distant planets.
I think the greatest promise of the James Webb Space Telescope is it will answer questions that none of us have imagined or thought to ask. And the discovery potential is huge, and I think it's going to have an amazing effect on humanity.
James Webb will go where no other telescope has gone before. We are going to try and see the first stars and galaxies and see how stars and protoplanetary systems were formed, which led to the formation of planets. We are going to see a lot more than we have seen before.
3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
The first conference to consider a telescope like Webb took place in 1989. Before the Hubble Space Telescope was even launched. This is because scientists already knew that if they wanted to see the faintest, earliest light of the universe, they would need a radically different type of instrument to Hubble.
Unlike Hubble, that primarily operated in the visible spectrum, in order for us to be able to see back in time to those very first galaxies, James Webb is actually going to primarily work in the infrared spectrum.
The photons that started off in the optical wavelengths that our eyes could see, because the universe is expanding, that light has shifted into the infrared. Its wavelengths have gotten longer. But that's a trick that Mother Nature played on us.
The first light that ever appeared was produced by the first stars and galaxies 13.5 billion years ago. Then, as the universe grew, this light became redder and fainter until it's now invisible to our eyes. But Webb is designed to overcome our limitations, to allow us to see what has never been seen before.
So it starts off really simple, but what that means is I'm looking at light that is very faint, comes from very far back in time. So I have to catch more photons. I need a bigger mirror. I need something 7 times bigger than Hubble. And once you start conceiving of that, you actually are designing a mirror that's bigger than the top of a rocket.
This was a challenge to our engineers to think of how they could produce the technology that the scientists needed.
The only way to make a very large telescope fit inside the nose fairing of a launch vehicle, in this case the European Space Agency's Ariane 5 rocket, is to make the instrument fold up like some enormous piece of origami.
So next thing you know, you're building a segmented mirror, a mirror in pieces that can fold up for launch, right, and deploy when it goes into space.
I'd already been talking to my friends here at Goddard about, can't we build a telescope that unfolds in space and maybe not too expensive? So my friends laughed at me because that was too hard. But now we're building one, and it is pretty hard. So this is a revolutionary concept. Nobody had ever tried it before, but I always thought we would find a way.
The mirror is built of 18 separate elements, each of which is made and installed with incredible precision to replicate a single large mirror that can reveal the tiniest of details.
It's like only 15 nanometers of error. It's the size of a bacteria. So that's so precise that I could find the heat signature of a bumblebee on the moon if I was using this telescope from Earth. Which means in our case, we can find a star that a photon came off 13.5 billion years ago. You know, that's what years of our lives have been put into.
The mirrors are fantastic. They are made out of a material called beryllium, which is 6 times stronger than steel, but only about the third of the density of aluminum. Having that strength also allows us to not deform, so that we can have a perfect flatness and take that perfect image of the distant galaxies.
But beryllium doesn't reflect infrared light that well. So we coat the mirror in gold, because gold reflects infrared. And it looks gorgeous, right? But we didn't build it to look gorgeous. It's actually functional.
The mirrors send light to 4 instruments, 2 cameras and 2 spectrographs that can analyze the chemical makeup of galaxies, stars, and the atmospheres of distant planets, looking for biomarkers, the chemical signs of life.
I would love if I could, tell my grandchildren, hey, I worked on that telescope, the one that saw the first biomarker on an exoplanet. Oxygen, and that oxygen couldn't have gotten there on its own. It was produced by some kind of organic life.
These instruments alone took years of experimentation and development.
Many challenges had to be solved. Maybe we underestimated some of those challenges in the early days. I'm sure we did.
But building the telescope is only the beginning. To be able to detect such faint light, the telescope must be kept very, very cold.
If you're going to build an infrared space telescope that wants to see, the first light that turned on in the universe, which is by definition the farthest things there are away, right? They're going to be very, very dim. Now, since they're very dim, you do not want that telescope to be glowing brighter than the very stars it's looking at. And things that are at normal temperatures, like here on the Earth, are glowing, intensely with infrared. So our telescope has to be extremely cold.
How cold? We're going to run this optic at minus 400 degrees Fahrenheit, which means I'm designing materials. Even glue that holds the structure together has to now work at cryogenic temperatures.
To keep the telescope cool, it must avoid the heat given off by the sun and the Earth, which drove many engineering choices. First, unlike Hubble, the Webb telescope could not be in low Earth orbit.
The Earth is so big and so close that it's shining heat radiation in all the time. So when you cannot make the telescope cold.
That's like, trying to keep a beer cold next to a blast furnace. So putting it in low Earth orbit would be make our thermal design for this observatory just more of a nightmare.
The solution is to send Webb out into deep space, 1 million miles from Earth, to a point called the Lagrange 2, or L2. This is a gravitationally stable place in space that Webb can circle as it orbits the sun with the Earth.
So what starts as this really, hey, just help me find out where did we come from and are we alone, leads to this massive engineering undertaking for a bigger mirror than humankind has ever put in orbit, flying it further away and operating it colder. And then with that, we started on a path of a decade long of invention.
There's a continuum of difficult things to make this mission reality. People thought we were nuts for even, embarking on this.
Even at 1 million miles from Earth, the heat of the sun would make the telescope useless, and the size and weight of the instrument ruled out using conventional cooling systems to keep it cold.
can't do that for a 6.5 meter optic. You can't put enough refrigerators up there behind it. You wouldn't launch them, they'd be too heavy, right? So we have to do what's called passively cool this giant optic.
We're going to do it just by pointing it into the blackness of space, let the telescope just cool into the darkness of space. That allowed you then to build this very big telescope, because if you're going to do it with liquid cryogens, you're going to have so much mass it was never going to be possible.
To protect Webb from the heat of the sun requires one of its most ambitious innovations, a giant sun shield, the size of a tennis court, made of 5 layers of reflective fabric, each as thin as a human hair.
The sun shield has been the source of so much of our efforts of late to get the telescope done and get it into space.
5 thin layers that have to be controlled and deployed in space. That is a challenge.
There has never been a spacecraft out there that has had such a large deployable sun shield with so many intricate steps. And it took a lot of technology, brand new technology, in order to develop the correct shape, the number of layers, the folding methodology, and even the deployment system is all brand new.
After launch, and while still on its way to its operating position, Webb will have to unfold this incredibly complex piece of equipment. Years of computer simulation and physical testing have gone into the design, but it's still a critical phase of the mission.
There's 178 release mechanisms on the James Webb, and they're responsible for initiating James Webb's unfolding sequence. All of these 178 release mechanisms are single-point failures, which means every single one of them has to work. And so we have one shot to make this right. It is a scary thought. I sleep better at night knowing that we've done everything that we can to make sure that James Webb is going to work right the very first time.
If it works as expected, the sun shield will offer extraordinary performance.
Around plus 200 degrees Fahrenheit, the sun is always hitting it, which is very close to the boiling point of water. And on the other side of this 5-layer umbrella that we deploy, it gets to minus 388, almost minus 400. We create a 600-degree Fahrenheit differential, which would be like putting sunscreen on at 1.2 million SPF, right?
With the design finalized and the major components built, testing the system proved to be one of the biggest challenges. At 1 million miles out, the James Webb will be too far away to be repaired or updated by humans, like the Hubble Space Telescope was. Everything had to be proven to work here on Earth.
We had learned from Hubble that one thing which was really important was to test out all the systems, including the optics. And so all that testing has to be done.
One of the hardest things engineers have had to do on Webb is work on the ground and simulate zero-G, because otherwise we're going to deploy something on the ground that'll either break because gravity will pull it out, or it'll give us a false feeling that it deployed, but only gravity pulled it out. Then I get on space and gravity isn't there. What if it doesn't open up on its own? Now, if you're an astronaut and you want to simulate zero-G, they do it a lot in pools, right? Well, I can't put the telescope in a pool. You know? So we have engineers literally designing things where we do counterbalance weights through a series of pulleys, and as we're driving the optic up alone, that's 8,000 pounds, we offload it, precisely pulls it with the opposite force of gravity. Otherwise, we could break it on the ground.
Another challenge was to confirm that the telescope could be adjusted and operated at cryogenic temperatures in a vacuum. So it was taken in its custom-built transporter to Houston, the site of one of the world's largest cryogenic vacuum chambers.
As we all know, shrinkage is a thing. When things get cold, they shrink, they get smaller, and when they get warm, they expand. Well, we're building this telescope at room temperature, but it has to operate at super cold temperatures. We actually had to build the optics and the structures that hold them exactly wrong at room temperature so that they are precisely correct, the cryogenic operating temperatures that they will be at. That's an incredible challenge, not only for designing and fabricating, but for testing. Because now to test this thing, I've got to put it into a big vacuum chamber. The relic of the Apollo era was refurbished to be this magnificent, cryo-optical thermal test facility, and suck all the air out, make the inside of that chamber really, really cold down to its operating temperature, and we can test and verify that, oh, yay, verily it does work at its cold temperatures. And that's really a point of achievement and pride, I think, for us.
The telescope was also subjected to multiple vibration and acoustic tests to make sure that it could withstand the shaking and the noise of being launched into space on top of a rocket. Finally, after even more testing, the instrument was approved in July 2021, 25 years and $10 billion after it was first proposed.
But we've done it. We have made this machine. We have brought the resources of NASA, of ESA and the Canadian Space Agency and all of the industries and all of the scientists, the engineers. We've made an astonishing machine. Here we are, and we're about to launch it. And it will just demonstrate that if you put your mind to it and you stick the course, you can achieve astonishing things. And that's a lesson which has applicability well beyond what you do in space with telescopes. It's a lesson for life.
The James Webb Space Telescope is scheduled to launch from French Guiana on an Ariane 5 rocket like this one in December.
My fantasy for that moment when it's all done is to just kind of sneak out of the control center. I just want to be alone. I want to get the biggest, fattest, stinkiest, ugliest cigar, smoke it with the ghosts of the Apollo engineers the way they used to do when their mission was successful. That's my fantasy.